But how did it all happen?
Sooner or later, after every accident, the inevitable question, who was to blame? The drivers themselves find it very difficult to be objective about what happened, and even unbiased witnesses find it hard to estimate speed and distance. So how does one get at the truth? In the accident we've just simulated, sadly, the Ferrari driver was killed. So, as there were no witnesses, the only version of the events is given by that driver of the second car, the Escort. According to him, he was coming up to the junction with this main road. He stopped, made sure the road was clear, and pulled out, when suddenly, from out of nowhere, and travelling at least 80 miles an hour, came the Ferrari. The two vehicles met at this point here, but the force of the collision was such that they bounced off one another, span across the road, landing up a good distance apart. If we wanted to predict these final positions of the cars from their initial speeds and directions, it would be relatively simple. But what's needed here is just the reverse, to reconstruct the events that led up to the crash from the clues that are left behind. And that means modelling backwards. It's vital to know just how fast the two cars were travelling and what the drivers were really doing. And that's what accident investigator Tom Ravensdale must discover.
And there we have the complete data on the Ferrari.
So you've got all the vital statistics of the car now up on the screen. Where do we go from here?
Well, we now need to know what sort of speeds are involved, what was the Ferrari doing and what was the Escort doing. So we'll go into a program which tells us the speeds of each vehicle after impact. And we want the post-crash distance of vehicle 1, which is the emerging car, which was 37 feet. Post-crash distance of vehicle 2 was 46 feet. The coefficient of friction of the road, which is the slipperiness of it, was 0.7. We established that from a test at the scene of the accident. The angle of approach, now they approached each other at 90 degrees. Post-crash angle of vehicle 1 was 80 degrees, and of the other vehicle, 65 degrees. Now, here we have the speeds. The Ferrari at impact was doing 50 miles per hour.
Oh, that's a lot less than this.
Yes, it is, because he's not a witness. And the speed of the emergent vehicle was 21 miles per hour. The next question to ask is, could he have reached 20 miles an hour at impact if he stopped? Did he stop?
Mm-hmm. So, Tom, what about the Escort? Did he stop at that junction?
No, he didn't. He couldn't have stopped and then accelerated to 20 miles per hour and 20 feet. It's just not possible.
So what about his version of the events? Was he mistaken?
It was certainly untrue, but he wasn't mistaken. No, I think he was lying, because from the angle of the crash and the speed, he must have been attempting to turn right, not left.
Jill Neville reporting. Now, Tom Ravensdale was using a perfectly ordinary home microcomputer to do his modelling on, so presumably we could do the same thing on our machine, could we, Matt?
Yes, we certainly could.
Well, I'm no great shakes at maths, so I hope it's nothing too harebrained complicated.
Now, well, I really love those old Victorian puzzles, and we've got one for you. It's really nice. Yeah. You've got a pond in your garden, an ornamental fish pond, and in it is 500 gallons of water, some carp, and a leak. And it's leaking at 1/500th of whatever's in it every hour. At 100 gallons left, your carp are going to die. How long have they got?
Fantastic. It's like an O-level question, isn't it?
It's not an easy question to answer.
No.
And what we're going to do is create a little model, and we're going to graph it something like this. And along the bottom here, we've got the hours that it's got, up to 1,000 hours. We're graphing it in hundreds along the bottom, and the water in gallons, running up here, 500 gallons. So let's just have a look at the program. Well, there's the subroutine that we've done for the graph.
That, yes, go sub 800 means that at number 800 in the program there is a subroutine which just draws that grid
That's right.
With
yes.
the markings, the number of
Yes.
gallons and the number of hours.
Right.
Okay.
Now here's a new one. Water equals 500. That's the 500 gallons of water that's in your ornamental fish pond to start off with.
Yeah.
And here we have one of these loops. For hours 0 to 1,000, we're going to draw our water. So for hour equals 0, hour here, we draw the point 0 and the water 500. So we draw the point 0, 500.
That's
now,
to make it draw that first
right,
point, which is
first
actually
point.
on the line of
Yes.
0 time. Okay.
Now we've got to calculate the next point.
Yeah.
First of all, we calculate the leak. And the leak is equal to the water divided by 500.
That means 1/500th of the water.
That's right. That's
Okay.
the amount that's leaked away.
Yeah.
So the new water, the water that's left in the tank after that first hour, this new water here is equal to the old water, which was 500, minus the leak. Of course, this water was 500 here, so the leak in the first hour was 500 divided by 500, which is 1. Right. So the new water with 500 minus 1, which is 499. And it goes back. It would plot that point, it goes back up here, and start to calculate for hour 1, and it would go through the whole routine 1,000 times.
Right. So the first calculation is quite straightforward. It's going to lose 1 gallon in 1 hour, isn't
That's
it?
right.
The next one is 499, and it's got to take a 500th of
that.
and subtract it from 499.
Right.
And that's a great deal
That's
more
it.
complicated. That's actually getting into long division already.
Already, yeah.
And it's going to make how many of those sort of calculations?
Make 1,000 of those, yes.
Right. And it'll
calculate the
happen,
position
it'll
of
happen in
1,000
seconds,
points.
I guess.
Well, we can do it. We just run it.
Right. Oh, there it's happening now. It's actually being calculated
It's
at this
actually
moment.
calculating
Yeah.
at this moment.
Right.
And that's the point where you're going to die.
This
That's
is,
the
no,
point.
right, this is, when we get down to 100 gallons of water, that's carp death.
But we can show it as it, I mean, this is not a representation of the pond. We can think in our imagination, we understand what's happening.
Yes.
But we can actually give you an idea of what it would look like in the pond itself. You see the time going down here, and the pond going out very quickly
That's
at
very
first.
clever. Look out, 100 hours coming up. I mean, 100 gallons coming up.
And there it goes.
Goodbye, carp.
Goodbye, carp.
That's terrific. Now, I can see that with sort of 2 elements coming together for the calculation, it's relatively simple. But obviously, in real life, in practice, it's never going to be quite as simple as that, is it?
Well, no, it isn't, because if it was real life, you'd have to take into account evaporation, and it might rain on the pond. You might have weed on the pond pressing it down, or not, as the case may be.
Yeah.
And you might even have a heron come along and eat your carp and allow the other ones to live longer, and so on and so forth.
So that's where computer power really comes into its own, is when you've got colossal amounts of data coming in to affect your final result.
Well, I think of it like the chess we were looking at the beginning. It's very easy to understand the rules, and in some of these models you can easily put the formulae together, but it's very difficult to know what emphasis to give to one particular set of rules and, you know, how they interact with each other once you set your model going again.
Well, thanks, Mac. A very good example of a really big computer model which most of us consult every day is the weather forecast. Now, we may not always get exactly the right answer, but when you think of the size of the problem, it's surprising that we get any answer at all. The European Centre for Medium-Range Forecasting at Shinfield provides a 10-day forecast to all the EEC member countries. The problem with predicting weather is making a realistic model of how weather systems develop and evolve on a global basis, and then supplying that model with sufficient observations of what is actually happening around the world. The model is numerical, a series of differential equations based on how we think the atmosphere works. It must take account of the forces that control weather, gravity, pressure, and friction, as well as atmospheric variables like temperature, wind, and humidity. To predict what might happen in any one part of the world over 24 hours requires an enormous amount of calculation, and it would be quite impossible without a computer, unless, of course, you wanted tomorrow's forecast sometime next week. The CRAIS period of prediction covers the whole globe for 10 days ahead, and the number of calculations that it performs is over 530 billion. And here's the 10-day forecast, which is the result. You can see how the isobars change from day to day. What you can also see is the enormous area the forecast covers, which may help to explain why the model gets the overall pattern right, but isn't so good at telling you whether it's going to rain in Romford tomorrow.